5-minute talk. Start with questions.
Hello. So shortly ago we heard about frogs and how they're such great jumpers. This is a video that I took from a presentation also from the Tom Roberts group. A couple of years ago they showed X-ray motion, X-ROM of a frog, and for the first time we're able to demonstrate experimentally this actual decoupling between the motion of a muscle driving a joint and the joint actually deflecting in an extension in a leap. And so, as you can see in this plot, there's about half of the motion that the muscle fascicles are going through during contraction is done before the joint starts deflecting at all. I like to term this power concentration, others say power amplification. Choose your poison. But the question we had was, what's the catch? As in, what enables this motion of the muscle to be separated from the motion of the joint when they should be linked just by a simple lever system? So humans, when we build things to amplify, to increase power output even in spite of a low actuator, like that device on the right from a lab in France, we usually use something like this big cam mechanism, or a latch or a trigger, something to hold the force and then let it go at a particular time. And there are a few examples in the animal world, including this locust that we saw there. I'll play that one again. And the click beetle up at the top that actually do this. They have a physical escapement mechanism or a latch to hold on to the power and then release it. But in vertebrates, there are no physical escapements that are known at this point. And so we wanted to address the question of how can you concentrate power without an escapement? So we proposed a mechanism to do that. Here it is. This is a simple 2-link robot model. These green things, they look beefy. They're actually light, very light in parameter. There's a heavy, relatively heavy motor that's also very low powered. You could specify any power, right? Well, we choose low power, and we put an elastic tendon and wrap it in a particular way around the joint, such that it has a very, very small moment arm about the joint when the joint is in this very flexed posture. You can see here, the robot that I'm going to show you has that number at about 1.5 millimeters radius. And you can see here in this diagram that with a body mass that is significant at some distance from the joint, the force that goes into that tendon has to be really large to overcome the moment due to body weight. Well, if you keep winding up that motor very slowly, eventually it hits that force and the joint starts to extend. When the joint starts to extend, these links, which were straight, begin to move over a little bit. The moment arm actually grows with a sine law as the joint begins to extend. So you can see that it grows very fast up in this diagram and ultimately gets to the whole thickness of those links. And you actually get a jump out of that. So with those ideas in mind, I give you RoboFrog. This is a simulation of RoboFrog. That purple line is the tendon winding up very, very slowly. And that's about a 40-to-1 power concentration with no physical escapement, no latch getting out of the way to release the energy. This is one video of a physical RoboFrog jumping. It's going to jump straight up here and do the same flip, a similar flip. Also with no escapements and a similar 40-ish to 1 power concentration ratio. Boy, oh, that's a minute, okay. There are a couple other videos. This is the effect of changing the compliance in the tendon. On the left, this is a stiff tendon. On the right, I'll go ahead and start that. There it goes. On the right is a tendon that's the same one I used in the previous video. You can see those rubber bands on the back. That's how we implemented it. Stretching very, very slowly. And very slowly indeed. And there's the jump and the flip, and it jumps about twice as high as in the other case. You can also get the frog to leap forward just by leaning it forward for takeoff. There's a long forward jump, 75 centimeters or so. And over on the right. You can do too much, and then it doesn't work. There are a few relationships here that maybe we can talk about during questions, but there are relationships between the moment arm, the spring stiffness, the height, the actuator speed. Higher, stronger actuator makes it go a little bit higher, but not a lot because of this nice concentration factor. And I leave you with this message. If a robot must take a big hop, it needs high acceleration from stop. A small spring tendon motor winding up on its rotor with a moment arm changing will pop. Any questions? Start over there, I guess.
Are you familiar with the work that was done in Caltech on this? They look basically nonlinear elastic behavior that would optimize the transfer of power from elastic storage to kinetic energy transfer.
Using a joint system like this?
No, I mean, it's related to this. And the way they do it is they use a parallel mechanism in order to use a linear spring and find a profile of power exchange from the elastic energy to the kinetic energy.
I'm not familiar with it. Yeah, I'll have to have you tell me more about it later.
Yeah.
Thank you. There was one in the back.
Have you observed this mechanism in any animals?
Not being an animal guy, I have not. There's some suggestion that it's not very much like a real frog, because we don't, the data I've seen suggests that there's no moment arm goes towards zero kind of effect in a real frog. However, I've been talking with Tom Roberts lately, and he says that might be changing, so we'll know later in the week a little more about that.
Okay. What happens if you don't have time to wait?
You're stuck.
So, can you postulate what's another mechanism that you might have to wait for?
Say that last part.
Is there some other mechanism like this that doesn't have,
It's a big time delay.
where you wouldn't have to wait?
So as you speed up the actuator that you're playing with, to the speed of a muscle. So we have this 20 or 40 to 1 kind of concentration ratio here. That's really extreme for purposes of demo. But if you speed up the actuator, you can do a lot better. So the frog had 2 to 1. You get the same power. Higher performance is always higher performance, I guess, is the message. And if you go into a higher speed kind of realm with your actuator, you can combine this geometric effect with a simple harmonic motion kind of mechanical filtering effect, so that even without a strange joint mechanics playing in, you can get most of the muscle motion decoupled from most of the joint motion just by the phase shift that you get from the spring and mass dynamics. Yes?
So some of your energy goes into rotation energy.
Into rotational, yes.
Is there a way to minimize that somehow?
Uh,
Are there any limitations in terms of how much is stuck with?
So the question is, how much goes into rotational energy, why, and can you minimize it? You're stuck with how much goes in there basically on the mass and inertia of the links. So ultimately, if you drive this moment arm sort of to a singularity point from one to another, it ends up accelerating very, very fast. And so those links are always going to do a snap motion. If you make them very light, there's not much energy there, and so it doesn't matter to you. In terms of the kinematics of this thing flipping over, that's another problem aside from the energy. And we think that you can add another link in the chain, possibly more than one extra link in the chain, and thereby, add an extra link in the chain and thereby sort of have 2 links cancel and get the thing to fly forward. Or you can move it out of plane. So this whole thing is extending in the same plane. If you have like a real frog, the legs splayed 45 degrees or more out to the side, then 2 of them would cancel each other out rotationally and you get a nice forward jump. So I think all these effects can be harnessed. Thank you.
So
Yes.
related to all these other questions, I mean, it seems like you'd like to reuse your high power muscles, your largest muscles for walking, you've got it sort of doing a special purpose thing. Is there any way to interleave this with stance control or something like this?
Absolutely. That's one of the beautiful parts of this design, is that it doesn't happen if you don't go to this extreme joint setting. So if you imagine the same joint that goes from fully flexed, I call that 180 degrees, to fully extended at 0, and your normal operating envelope is between, say, 0 and 45, then the moment arm ratio you're playing with is, instead of 0 to 1, it's more like 0.8 to 1. And you basically control it like a constant moment arm joint. So you can use the same actuator 90% of the time for walking or whatever, that way, and then squat and jump if you need to. Thanks, everyone.
Thanks.